Welcome to Module 40 in this series of lectures on statistical process improvement and statistical quality assurance. This is the second lecture on so-called statistical, or more properly probabilistic, tolerancing. This is the set of examples of using this methodology that was introduced, the methods introduced in the previous module. Returning to the box packing example, it was the first example in module 39. Remember, this is the scenario in which one needs to put 4 units of product into a carton, and the headspace in the carton is the difference between the inside length of the carton and the sum of the sizes of the 4 units put into the carton. That is, it is y minus x1 minus x2 minus x3 minus x4. If one takes the form then for the variance of a linear combination of the x's and the y, the variance for the headspace is the variance for y plus the variance for x plus the variance for x plus the variance for x plus the variance for x, because the coefficients in that linear combination are all 1s and minus 1s, and by the time they get squared, the sign doesn't matter. The student team that worked on that project determined that the average inside length of the carton was about 9.56 inches and the standard deviation was about 0.053 inches. That the average size of a unit to be packed in the carton was about 2.58 inches and the standard deviation was about 0.061 inches. So if one then takes essentially one of these squared and 4 of those squared, one gets a variance of about 0.0177 inches, or a standard deviation for the headspace of around 0.13 inches. There's not much variation on the on any of those variables, the inside size of the carton or the size of the units of product, and so all combined, that's not much variation for a standard deviation on the headspace. However, if you take the mean inside dimension of the carton and you subtract the average for x1, subtract the average for x2, subtract the average of x3, subtract the average of x4, you get about minus 3/4 of an inch. That is, the mean headspace in those cartons was negative, and it was then, by the time you combine that with this, it was essentially guaranteed that there was going to be an interference in packing those units into those cartons. If you didn't want interference, if you didn't want a large probability that the headspace is negative, then what would be required would be to adjust the average unit size downward, or the inside dimension of the carton upward. With this kind of analysis, you can think about the various costs of making those changes and what that will do to the packing of if one makes various kinds of changes. As a second example, consider this basic physics example where one is going to put resistor 1 in series with a assembly of resistors 2 and 3 that are in parallel to produce an overall resistance predicted from basic physics to be of this form. If one takes partial derivatives with respect to R1, with respect to R2, with respect to R3, one gets these formulas. And if one then thinks about making an assembly with, say, resistor 1 having resistance with mean 100 ohms and a standard deviation of 2 ohms, while resistors 2 and 3 each have means resistances of 200 ohms and standard deviations 400 ohms, then the overall assembly will have average resistance around what you get when you take the formula for resistance and plug in means. So I plug in 100, I plug in 200 twice, and one gets about 200 ohms for the assembly. The standard deviation for the resistances, one takes this partial derivative and squares it. One takes this formula for partial derivative and plugs in R mean for R2 and R3 and squares it. One takes this formula for partial derivative and plugs in R2 and R3 and squares it, and then multiplies by variances, adds, and takes a square root to get about 2.54 ohms for a standard deviation of assembly resistance predicted by this this kind of analysis. To see how easy it is to do simulations to get similar, or to get the results without having to do calculus, these panels show the use of jump to make values for R1 and make values for R2. I've not included R3, but one it's just like R2, and then how it is having columns for R1, R2, and R3 to make values for R, the overall resistance. And then if one makes 1,000 such things, makes a table with 1,000 rows in it, one can just use basic summary statistics from the statistical package to get values similar to the ones here. To see that, here's the jump table with values of R1, R2, R3, and R. There's 1,000 rows here. You can see that right there. Here is a histogram of the simulated resistances for the assembly. And here's a mean that is very close to 200 ohms, and here's a standard deviation that's very close to this figure 2.54 that we got by pencil and paper kinds of calculations. To finish off this set of examples, we could go back to that car door example. I haven't put that slide in here, but you can go back to module 39 and see that there were inputs X, Y, W in 3 different angles. And here's some Minitab code for making variables 1 through 6 and simulating normal variables 1 through 6 with means and then standard deviation. So mean 90, standard deviation 0.01, mean 90.4, standard deviation 0.01, and so on. If one then follows through that set of equations in the previous module that relate the gaps to the inputs, one can do descriptive statistics and get summaries of the simulated values. And for the particular kinds of tolerance budget that was implied by these means and standard deviations in the simulation, the average gap number 1 is about 0.4 inches, average gap number 2 is about 0.4 inches. You can see that gap number 2 is more variable than is gap number 1, and if you go back and look at the geometry, that's perfectly plausible. The take-home message here is that these methods of probabilistic tolerancing are really quite powerful tools for understanding consequences of various levels of input variation on output variation, system variation, how that system variation depends upon component variation. Very important engineering design tools, important for making products that are not highly variable, by making intelligent choices about variation budgets, tolerance budgets for the components of those products.